Let's think about transformations of scale when it comes to the standard deviation. I want to illustrate two things. One is that adding a constant to each score does not change the standard deviation. And then number two, of course, multiplying each score by a constant does change, and it will be multiplied by that same constant. Let's take a look at the first example. If you see the numbers on the left, those are numbers that we've gotten used to. 8, 6, 4, and 2. You might remember a few slides ago, we calculated the variance as being 5. We went through that whole calculation, and sure enough, the standard deviation is the square root of 5, which of course is 2.24. In the right-hand example, you'll see that a constant of 20 is added to each number, which is, pretty self-explanatory. But then you have to ask yourself, well, wait a second now. Is it the case that the numbers are more spread out, or did they all move down the number line together? And the short answer is they all move down the number line together. As you can see, there's no more spread between the numbers. In fact, the range is roughly the same, which is roughly 6, 28 minus 22, or if you want to frame it as 28.5 minus 21.5 or 7, doesn't matter. In that case, you've got the same spread of the numbers, so the standard deviation doesn't change. And indeed, if you went through the math would turn out precisely the same. So you just see the spread of the numbers hasn't changed. It just got shifted down the number line, and therefore the standard deviation is the same. However, when we multiply by a constant, it does change it. We've got our first numbers there, 8, 6, 4, and 2. Fair enough. What about if we multiplied by 10? Holy cow. I hope you'll agree now that I've exploded the distance between the numbers. Instead of being roughly 2 apart with each progression, now they're 10 apart. Big difference. And as the rule says, the new standard deviation is going to be roughly tenfold the one that came before. It's going to be, instead of 2.24, 22.4, and that's roughly what it is. It's actually 22.36, but we're doing a little rounding here. But I went through all the math and calculated the average deviation, which is always 0, and then I squared each deviation and got a total of 2,000, which is a big number. I got my sum of squares of 2,000, divided that by 4, and got a variance of 500. And sure enough, the square root of 500, as you knew off the top of your head, was 22.36 actually. But again, due to rounding. So, but never mind the math. Forget that. I just want you to believe this principle because I can just see that the distance between 80 and 20 is a range of roughly 60, or if you want to say 61, 80.5 to 19.5. It's much bigger than, of course, from 8 to 2. And therefore, we would assume it's a much larger standard deviation. Of course we would. So in that case, we got a variance of 500. And, of course, the standard deviation is exactly 10x. It's 10 times 2.24 with 22.4.